What do an old iron and thousands of dollars have in common? That is right, copper. You know, just from one single cord, you can pull out enough copper to make brand new electronics. Every day, tens of thousands of old irons are recycled around the world, taken apart down to the very last screw. But how exactly does this happen? Why can even the Soleplate be dangerous? And what is hiding inside the heating element? I am about to show you how dead irons come back to life, from being taken apart to becoming valuable raw materials. Like other electronic appliances, irons are accepted at special electronics collection points. There, they are sorted into categories: those that can be repaired, those that need to be disassembled for parts, and those sent for complete recycling. Worn out or non-working irons are sent to recycling facilities, where the disassembly process begins. When an iron arrives at the disassembly line, specialists wearing protective gloves check it over. Some parts, like the heating elements, can be hazardous due to residual electrical voltage or toxic substances. First, they remove the electrical cord. Its insulation is usually made of synthetic plastic or rubber, and inside there is copper or aluminum wire. Synthetic plastic is durable, flexible, and water-resistant, but when heated or burned, it can release toxic substances, including dioxins, which are harmful to the environment and human health. That is precisely why disposing of it requires special methods. The removed cord is not just set aside. It immediately goes onto a sorting line. First, it is chopped up in a special shredder into pieces about 1 to 2 inches long. This makes it easier to separate the metal from the insulation later on. Next comes the material separation. This is usually done using mechanical or electrostatic sorting methods. What does that mean? What kind of fancy words am I throwing at you here? Look, the copper and aluminum wires are separated and sent off to metallurgical plants for melting. The shredded plastic or rubber goes for recycling, for example, to make new cable insulation or other products. If the insulation contains harmful additives, it might be incinerated in special furnaces equipped with filters or sealed away in a landfill. Separating the copper and aluminum from the shredded electrical cords happens in several stages. So, after the cord is shredded, the pieces are sent to a granulator. This is a special grinding machine that breaks down the pieces of wire into even tinier particles, measuring about 4/100ths to 8/100ths of an inch across. This is how the metal and plastic get separated. Next, the mixture goes into an air separator. This uses a stream of air that lifts the lighter particles up, while the heavier ones fall down. This way, the plastic is separated out even before the main process. If there are any steel components in the wires, like a thin shielding layer or reinforcing fibers, they are removed using a magnetic conveyor belt. But the tricky part is, the little pieces of aluminum wire and copper wire get mixed together, so now they need to be separated. To do this, the metal particles are sent into a metal drum that is charged with high voltage. Copper has different electrical conductivity properties than aluminum, so under the influence of electrostatic forces, they bounce off in different directions and are collected in separate containers. After sorting, the materials are checked again, either by hand or using automated systems. Copper, which is 99% pure, is melted down at a temperature of 1979 degrees Fahrenheit and used for new cables. Aluminum melts at 1220 degrees Fahrenheit and is used to make parts or casings for electronics. This process allows up to 95% of the metals from the cords to be reused, reducing the need to mine new raw materials. Meanwhile, back at the iron, the housing is unscrewed. This could be a plastic or metal shell, depending on the model. A worker wearing gloves firmly secures the device on a table coated with a thin layer of metal shavings, leftovers from previously disassembled appliances. An automated screwdriver mechanism, humming almost silently, moves toward the first screw. The bit fits precisely into the screw head, makes a few quick turns, and the loosened screw flies out into a special container, clinking against the sides. The housing still holds on, as if resisting its fate. But the hands of the technician, seasoned by thousands of these operations, know how to make it give way. A slight pry with a tool under the edge of the housing, and there is a familiar click, like an old machine sighing. The plastic cracks, yields, and then splits into two parts, revealing the device's insides. If the housing is metal, it all happens with different sounds. The metal screws fall heavier. The housing slides across the table with a dull clatter. Sometimes, special cutters have to be used. Sharp blades sink into the thin metal, leaving behind jagged edges that glint under the lights. Finally, the shell is removed, and the device, just a moment ago solid and sealed, seems almost vulnerable. Its insides exposed, ready for the next stage of disassembly. Once the housing is off, the heart of the device is revealed. The circuit board and the heating element connected by a network of thin wires. They are like the veins that powered the appliance in its former life. Tweezers with pointed tips move towards the first contact point. A gentle tug, and the wire pulls away from the board with a faint snap, exposing a tiny copper core. Another tool, resembling a miniature pry bar, slips under the edge of the board. A little pressure, and the board pops out of its place, leaving behind a web of connectors and mounting points. The heating element is the next hurdle. If it is ceramic, it sits inside like a white heart, sometimes coated with a grayish film from countless heating cycles. If it is a nichrome coil, it is wound into a delicate spring, resembling a dried leaf. It is removed carefully to avoid damage, because even the smallest break can complicate further processing. And just like that, with a few more movements, the once unified mechanism falls apart into separate components. The circuit board and heating element are separated, ready for sorting and further processing or disposal. The last part holding its ground is the Soleplate. It has absorbed thousands of heating and cooling cycles, signs of use, scratches, and faint traces of scorch marks. It is the sturdiest part of the device, and removing it is not so easy. To get it off, they take a tool similar to a thin pry bar and wedge it between the main body and the Soleplate. A barely perceptible push, and you hear a characteristic scraping sound as the metal begins to yield. If the Soleplate is aluminum, it bends under pressure, making a slight crunching sound. A ceramic one stays put until it gets a precise tap, after which it separates from the body with a muffled thud. If it is stainless steel, it puts up the most resistance. It often has to be unscrewed by hand or pried off using special levers. Finally, the Soleplate is detached. It drops onto the metal table with a dull thud, leaving traces of grime on the worker's fingers. This is the last major piece, and now the appliance is completely disassembled, ready for further sorting and recycling. Ever wonder where your old laptop goes after you toss it out? Every single year, millions of tons of electronics like these end up getting recycled. But hey, it is not just trash. Inside, there is a real treasure trove. Gold, silver, copper. And right alongside that, toxic hazards, mercury, lead, and batteries just waiting to burst into flames at any moment. How do they protect your data on those old drives? Why are the workers dressed like astronauts? See for yourself the shocking but super important journey your old gadget takes, from the conveyor belt all the way to extracting precious metals. It is a sight that will totally change how you think about unwanted electronics. Keep watching. Specialized companies or collection points take in old laptops from regular folks and businesses. The devices get checked to see if they still work. Laptops that are still working might get fixed up and resold, or donated to charities. Large batches of laptops are transported to specialized facilities. There, trucks unload containers full of laptops. Workers using forklifts move them to the sorting area. Then, workers wearing protective gloves and special suits look over each laptop. Yeah, safety is a really big deal here. The people on the sorting line wear protective gloves and suits for a few reasons. Old laptops might have components containing lead, like in the solder, or mercury in the fluorescent backlights of the displays. Touching these without protection could lead to poisoning. Cadmium and beryllium are dangerous if they touch your skin or if you breathe in the dust. These heavy metals are used in batteries and circuit boards. Some laptop parts, especially broken screens, can have sharp edges that could easily cut your hands. And during disassembly, small components can break off and go flying. Even when a laptop seems dead, some capacitors can still hold a residual charge. Touching them without protection could give you an electric shock. Special anti-static suits and gloves prevent damage to electronic components from static electricity. When the laptops are shredded, a lot of toxic dust is created, which can contain microscopic particles of metal and plastic. To avoid breathing this dust in, workers wear masks or respirators. Working laptop models are set aside during sorting. They can be repaired and sold. The rest are sent off for recycling. Lithium-ion batteries are removed by hand because they can catch fire or explode. During shredding, or if they get damaged mechanically, the battery can overheat and ignite. Lithium reacting with air or water can release flammable gases. Also, inside the battery, there are toxic electrolytes that can cause chemical burns or poisoning. If a battery gets deformed, these substances can leak out and get into the environment. That is why workers manually unscrew the panels and take out the batteries. If the battery is built in, they disconnect it using a special tool. The removed batteries are placed into heat-resistant containers filled with sand or other non-flammable materials. They are stored in well-ventilated areas, away from other waste materials. Recycling the batteries happens separately from the rest of the laptop. They go to specialized plants where the metal casings are shredded. From the internal materials, like nickel, cobalt, and lithium, useful components are extracted for reuse. After the batteries, the next critical step is removing the hard drives. Why are hard drives taken out separately? Well, the thing is, even if the laptop does not work, data can still be stored on the drive. And corporate or government laptops might contain sensitive data, so the hard drives have to be destroyed following special procedures. Some drives have moving mechanical parts, like platters and motors, which are processed separately. Other drives are made of memory chips that need a different recycling technology. Workers unscrew the laptop casings and remove the drives by hand. In some models, solid-state drives are built right into the motherboard. In that case, they are either desoldered or broken off along with the board. After that, there are 3 ways they physically destroy the drives to ensure data security. They are either shredded in special shredders, turning them into tiny metal fragments, or they are wiped using magnetic degaussers, which erases the data permanently, or they are melted down into metal ingots. The aluminum casings from hard disk drives are sent off for remelting. The magnetic platters have coatings of gold, platinum, and cobalt, which are extracted using chemical processes. Solid-state drive controllers contain copper, silver, and rare earth metals. These are also extracted for reuse. Once the batteries and hard drives are out, the laptops do not pose a serious fire or data security threat anymore. Now, they can be sent over for automated case disassembly. The laptops move along a conveyor belt, passing one by one under an automated press. Powerful hydraulic plates with up to 5 tons of force squeeze the casing, causing tiny cracks in the fasteners. One hit, and the top panel separates from the bottom, leaving the internal components accessible for further processing. The laptops keep moving down the line. Mechanical arms with thin metal fingers hover over them. Each arm is equipped with an automatic screwdriver unit that spins at up to 5,000 revolutions per minute. In just 4 to 6 seconds, the robot unscrews the screws and carefully removes the keyboard, speakers, and cooling system heatsinks. When the laptop reaches the next module, 2 pneumatic grippers grab onto the screen. A blade with a high-precision control system runs along the edges, cutting through the plastic fasteners. A barely audible crack, and the display is separated. Now the laptop is almost empty, with only the main guts left, the motherboard. Another arm removes it, using vacuum suction cups to lift the board and place it into a separate container. The whole process takes less than 2 minutes, and what was once a whole laptop is now just separate parts, ready for sorting and further recycling. The conveyor moves the separate laptop parts to sorting stations. Both robots and people work here. Plastic case panels are directed one way. They pass through special scanners that identify the type of plastic. Some types of plastic can be reused. Others are disposed of as regular waste or converted into fuel for industrial plants. Metal parts, like case frames, fasteners, and heat pipes, go through magnetic separators. Ferromagnetic metals, like iron and steel, are separated using powerful magnets. Non-ferromagnetic metals, like aluminum and copper, are sorted using induction detectors. Glass from the display screens goes into a shredder, where it is broken into small fragments. After that, special equipment cleans the glass granules of impurities. The resulting material can be used to make new displays or building materials. Motherboards, graphics chips, processors, and other integrated circuits are collected separately. They are checked to see if they can possibly be reused. If the circuits are still usable, they are sent to the secondary market or for refurbishment. Most electronic components, however, end up being recycled. To do this, they are sent to special furnaces where high temperatures burn off the organic materials. Only the metals remain: gold, silver, copper, palladium. They are extracted using chemical methods, purified, and returned to manufacturing. Laptops also contain hazardous substances: lead, mercury, cadmium, lithium. These cannot be allowed to enter the environment, so they undergo special processing. The fluorescent lamps from displays, which contain mercury, are separated under sealed conditions so that mercury vapor does not escape into the air. The recovered mercury is reused, for example, in medicine or in making thermometers. The lithium batteries, which were removed in the initial stage, are transported to separate plants. There, they are dismantled, and lithium and other useful elements are extracted. The resulting materials are used in the production of new batteries. Lead, found in solder, is melted down under controlled conditions, separating it from impurities. The entire process of dismantling, sorting, and recycling a laptop can take anywhere from a few hours to several days, depending on the scale of the facility and the technological process used. After sorting, all the materials are distributed into separate containers, or large industrial bins, depending on their type and the next steps in processing. In the plastic containers, you will find fragments of casings, keyboards, touchpads, which might be black, gray, or silver. The plastic is sorted by type: acrylonitrile butadiene styrene, polycarbonate, polypropylene. In the bins for metals, you can see piles of parts. Here lie aluminum frames and lids from laptop cases, copper heat sinks and wires, steel fasteners and screws. Containers for electronics are filled with the removed motherboards, graphics chips, random access memory modules. It all looks like a heap of complex green and blue boards with gold contacts and copper traces scattered across them. In separate containers for displays, there are dismantled screens with fragments of glass and metal frames. Sealed containers for hazardous materials hold batteries. Mercury lamps and capacitors containing lead are stored separately. These are often kept in special zones with warning signs about toxicity and explosion risks. After sorting, all these materials need to be transported to specialized plants where they will undergo further processing and preparation for reuse. To save space in trucks and containers, some materials are compressed. For example, plastic is shredded into granules or pressed into large bales. Metals are compressed into dense cubes. Glass is crushed and packed into bags or containers. Electronic components are stored in large containers without being compressed, since they still need to undergo chemical treatment. Lithium batteries are placed in special non-flammable containers, often filled with sand or expanded clay pellets to prevent ignition. Mercury lamps are transported in sealed boxes that prevent mercury vapors from getting into the air. The materials are loaded onto trucks, trains, or ships, depending on the distance and the type of material. Large metal cubes are lifted by forklifts and stacked in trucks. Containers with plastic and glass are transported in trailers or sea containers. Electronic components might be transported in special containers with shock-absorbing protection. Metals are sent to metallurgical plants, where they are melted down and purified. Aluminum, Copper and iron can be reused in manufacturing electronics, cars, or building materials. Plastic goes to plastics recycling plants, where it is shredded, melted down, and used to produce new casings for electronics, furniture, or packaging. Glass goes to facilities that manufacture new screens or building materials, for example, insulation made from recycled glass. Electronic circuit boards are delivered to plants specializing in extracting precious and rare earth metals. There, the integrated circuits are dissolved in chemical solutions to extract gold, silver, palladium, and other valuable metals. Batteries head to facilities where lithium, nickel, and cobalt are extracted for manufacturing new batteries. Hazardous waste goes to special landfills or chemical plants, where toxic substances are neutralized or rendered harmless under controlled conditions. After several months or even years, the materials from a recycled laptop can end up back in production, as part of a new device, building, or car. Some large recycling facilities specialize narrowly, for example, dealing only with computer equipment or mobile devices. Others recycle almost all types of electronics, including large household appliances. Every single year, more than 200,000 hydrocycles are sold all around the globe, and the overall market for this type of equipment exceeds $2.5 billion United States of America dollars. But how does a piece of composite material turn into a genuine water monster that can accelerate up to 70 miles per hour? What makes the Japanese Yamaha factory the largest hydrocycle manufacturer in the entire world? From automated hull molding to the most advanced engines and on-water testing, today we are going to unveil every secret of their production. Fasten your seatbelts, because we are heading into a realm of high speeds and groundbreaking innovations. The design of hydrocycles begins with conceptual ideas and essential requirements for technical specifications. The very first stage involves identifying the target audience and the purpose of the hydrocycle. It can be a recreational model, a sports or extreme hydrocycle, or even specialized versions for fishing or rescue operations. Designers and engineers must consider not only the visual appeal, but also factors such as maneuverability, stability, top speed, comfort, and water safety. They carefully think through each detail so that the final product meets the needs of both beginners and seasoned riders. According to Statista, the global hydrocycle market by the year 2027 will grow to over $2.5 billion United States of America dollars, with an annual growth rate of 8.3%. This impressive forecast shows just how much interest hydrocycles continue to generate in different parts of the world, especially as new technology makes them more efficient, eco-friendly, and fun to ride. One of the biggest markets for hydrocycles is the United States of America, where more than half of all hydrocycles worldwide are sold. This country remains a leader in water sports development, partly because of its numerous resorts, lakes, rivers, and coastlines, which make hydrocycles immensely popular among both local residents and tourists. Hydrocycles are also well liked in Australia and Japan, where water activities are an integral part of cultural traditions, and people love to explore different forms of aquatic adventure. During the development stage, important factors include the design of the hull, which must be light yet strong and resistant to mechanical damage. For this purpose, high-quality materials such as fiberglass, composites, and aluminum are used to achieve the required rigidity without adding too much weight to the hydrocycle. Another critical consideration is the choice of engine. Most hydrocycles use internal combustion engines, although a growing number of manufacturers are experimenting with electric models, which offer cleaner emissions and produce less noise. In modern hydrocycle design, special attention is paid to innovative technologies, including digital control systems, integration of the global positioning system, and sensors for monitoring the condition of the equipment and improving navigation. These features not only make the experience more convenient for the rider, but they also boost overall safety through automatic stability control systems or engine rotation alerts. All of this simplifies the hydrocycle piloting process and makes it safer, even for first-time enthusiasts. The United States of America holds over 50% of the global hydrocycle market. Another notable trend is the rising demand for electric hydrocycles. Although they currently occupy only a small share of the market, their environmental advantages could make them a key part of the hydrocycle industry's future, since they help reduce emissions and lower noise pollution levels on the water. An essential element of design involves creating an ergonomic layout that ensures comfort during lengthy rides or races. Seats must be comfortable and provide proper support for the rider's posture, while also featuring a non-slip surface that holds up in wet conditions. Additionally, hydrocycles are equipped with various features, such as extra storage compartments, waterproof pouches, and cooling systems that help the vehicle operate at high revolutions over long periods. Developing new models also requires numerous water tests to check how the hydrocycle performs in real conditions. This process helps identify any weaknesses in the design or technical parameters, which are then corrected before the start of mass production, guaranteeing that customers receive a high-quality product. The hydrocycle development process is extremely detailed and demands meticulous attention at every phase, from designing the hull to testing the final product. Engineers, designers, and manufacturing specialists must work in close collaboration to produce equipment that is not just powerful and fast, but also safe and comfortable for users. Hydrocycles need to be easy to maneuver on the water, while also having enough durability to withstand heavy loads, water pressure, salt, ultraviolet radiation, and other environmental factors. These stringent requirements mean that the choice of materials for different hydrocycle components must be carefully evaluated to balance weight, strength, and resistance to corrosive elements. First and foremost, a key element of any hydrocycle's construction is its hull. This is one of the main parts that must be strong enough to resist mechanical damage and, at the same time, provide optimal hydrodynamic characteristics. The most common materials for hull manufacturing include fiberglass, composite substances, and aluminum. Fiberglass is selected because it offers high strength at a low weight and is resistant to corrosion, making it ideal for use in aquatic environments. In addition, it can be molded easily, allowing engineers to create sleek aerodynamic shapes for the hydrocycle hull. Composite materials, which include polymers reinforced with fibers such as carbon or Kevlar, are even more advanced, delivering greater strength while reducing weight. They also exhibit excellent resistance to ultraviolet exposure and chemical agents like salty water solutions. By combining these materials, manufacturers can cut down on hydrocycle weight while improving speed and maneuverability, which is especially beneficial for sports-oriented models. When it comes to internal components, such as fuel tanks and cooling systems, manufacturers often rely on stainless steel or specialized plastic blends. Stainless steel is a long-lasting material that resists corrosion, making it perfect for repeated contact with water and various liquids. Plastic blends, such as high-density polyethylene, are used due to their lightness, durability against chemical and mechanical impact, and ability to function effectively for extended periods in high humidity conditions. Another crucial consideration is the choice of materials for hydrocycle engines. Lightweight yet powerful substances are essential for achieving high revolutions without sacrificing endurance. Typically, engine components are made from metal alloys, including aluminum, titanium alloys, or magnesium. These materials have low density, which helps reduce engine weight, and they have excellent thermal conductivity, which is critical for efficient cooling and overall engine performance. One well-known hydrocycle manufacturing facility is located in Japan, operated by Yamaha Motor Company, which is widely recognized as one of the leading brands in the watercraft market. Situated in the city of Iwata in Shizuoka Prefecture, this factory produces not only hydrocycles, but also other types of water transport and their engines. The Yamaha Motor Factory spans approximately 250 acres, making it one of the largest facilities in the world dedicated to water equipment production, including hydrocycles. The site specializes in manufacturing a broad range of water transport products, including diverse hydrocycle models, boats, yachts, and other motorized water vehicles. Every year, this factory turns out thousands of products, including over 60,000 hydrocycles annually, which secures Yamaha a substantial market share in the water transport sector. Thanks to the factory's expansive premises, every stage of production, from assembly to testing and packaging, can be carried out efficiently and in one location. One of the main automated lines is responsible for forming hydrocycle hulls using materials such as fiberglass and composites. This line is equipped with robotic arms that precisely shape and join individual hull components, delivering the exact design contours and a smooth exterior finish. In addition, automated welding and painting systems are used to process metal parts, such as engines and their subsystems. The line features robotic welding machines that provide accurate, high-quality welds, as well as automated painting systems that evenly coat components and offer reliable protection against corrosion. This advanced technology helps ensure the product maintains a pristine appearance and robust structure over an extended service life. The assembly lines have a real-time quality control system, which automatically identifies defects at any stage of production. This includes visual inspections using cameras and scanners capable of detecting even the smallest flaws in parts, allowing the factory to preserve the highest possible product quality. A distinctive feature of this factory is its extensive automation in the packaging and shipping phases. Once hydrocycles have passed all quality checks, they move on to automated packaging lines, where robotized systems assemble boxes and secure the hydrocycles inside transport containers. This process enhances shipping safety and streamlines logistics, ensuring that the products are delivered to customers in excellent condition and on schedule. The Yamaha factory continuously adopts the latest technologies in water equipment production. For instance, they use three-dimensional printing to create prototypes of new models, enabling faster testing and refinement of their designs. Moreover, the facility employs pioneering materials that help reduce the weight of hydrocycles, increase their corrosion resistance, and extend their service life. They also make active use of intelligent production management systems, which optimize manufacturing processes, cut down on costs, and shorten the time needed to produce each unit. As a result, the factory can expedite hydrocycle manufacturing and boost output volume, illustrating Yamaha's commitment to continuous innovation and leadership in the fast-paced world of hydrocycle development. Every year, between 80 billion and 150 billion units of Adidas clothing are produced worldwide. But what about footwear, which holds the second largest production volume in the world? Recently, Adidas has seen a significant surge in popularity for its retro models, such as Samba, Campus, and Handball Special. According to the online platform StockX, Adidas sales increased by 51% compared to the previous year. Let us dive into the production of these legendary sneakers and see how new footwear is brought to life. The process of creating a new Adidas shoe model begins long before the first physical samples reach the production line. Dozens of specialists from different fields take part in this process. Designers, marketers, engineers, technologists, and even sports consultants. Adidas designers constantly analyze market trends, researching which models are currently in demand, which technologies are evolving, and what consumers prefer. This includes analyzing past sales data, studying fashion trends in streetwear and sportswear, monitoring competitors such as Nike, Puma, and New Balance, tracking new materials and innovations in manufacturing, and conducting surveys with professional athletes and regular users. This process can take anywhere from several weeks to several months, depending on whether it involves updating an existing line or creating an entirely new concept. Once the team gathers enough information, the concept development phase begins. Designers create the first sketches, plan the shape, position logos, and select material and color combinations. At this stage, it is crucial to find the perfect balance between style, functionality, and comfort. Interestingly, Adidas frequently uses specialized three-dimensional modeling software that allows designers to create realistic digital images of future shoes. This helps save time and provides a more accurate visualization of how the model will look in reality. This exciting process can involve anywhere from 10 to 50 people, depending on the complexity of the project. This includes not only designers, but also biomechanics specialists who assess comfort and foot impact, technologists responsible for materials, and even marketers who propose changes to meet consumer expectations. Designers may suggest a stylish solution, but if it is uncomfortable or does not meet technical requirements, such as weight, material durability, or breathability, it must be revised. Some ideas are impossible to implement due to technological constraints or excessively high production costs. Adidas is actively working to reduce environmental impact using recycled materials and eco-friendly technologies, which also influence design decisions. After the first physical prototypes are created, Adidas puts them through rigorous testing to evaluate comfort, durability, and compliance with stated characteristics. This stage assesses material quality, seam strength, and overall resilience before launching the model into mass production. Shoes are placed in specialized machines that simulate walking or running through thousands of cycles to test the wear resistance of the sole and upper materials. The sole bends thousands of times to check for cracks or deformations. The shoes are submerged in water or exposed to moisture to test their resistance to soaking. The force required to tear fabric, seams, or glued elements is measured. Adidas employs robotic systems that replicate real-life usage conditions. Special robots simulate foot movements during running, jumping, and sharp turns. Shoes are subjected to extreme temperatures to assess material behavior. Shock absorption and impact resistance are analyzed using sensor platforms. No footwear enters mass production without undergoing real-world testing. Adidas collaborates with professional athletes who wear new models during training and provide feedback. Key testing aspects include comfort during running, jumping, and prolonged wear, foot and ankle support, breathability, and adaptation to different surfaces such as asphalt, grass, and hardwood floors. All these stages can take anywhere from several months to a year, depending on the model's complexity and the number of necessary adjustments. If a prototype fails testing, it returns for further refinement. Adidas works with suppliers worldwide. For example, the Boost sole was developed in collaboration with the German chemical company BASF. This revolutionary sole consists of thousands of expanded thermoplastic polyurethane pellets that provide high energy return. Once all necessary materials arrive at the manufacturing facility, one of the most crucial stages begins: cutting and preparing shoe components. From large fabric or leather rolls to sheets of synthetic materials, all components are placed in designated cutting zones. Workers or automated systems load materials into cutting machines according to the production plan. Modern Adidas factories use automated feeders that evenly unroll fabric or rubber for precise cutting. Laser cutting is used for thin synthetic materials and mesh fabrics like prime knit, as well as for intricate designs requiring high precision. Mechanical cutting is performed using press cutters or automatic knives following program templates. This method is ideal for leather components and thick fabrics. High-precision computer numerical control cutting machines can simultaneously cut hundreds of pieces from different materials, significantly accelerating the process. To minimize waste, software analyzes the most efficient way to position shapes on the material. Leftover scraps from cutting may be used for smaller components or other shoe models. Some recycled materials, such as Parley Ocean plastic, undergo secondary processing for reuse in future products. After cutting, components undergo additional technological treatments to achieve the required properties. Lamination is used to reinforce fabric and improve its performance characteristics. For example, running shoes may feature multi-layer lamination to enhance waterproofing and durability. This process includes applying special polymer coatings or thermal adhesives to increase material strength. Some shoe elements, especially those containing thermoplastic components, go through a heat molding process. When heated to a specific temperature, the material becomes pliable and takes the desired shape. Once cooled, it retains its structure. This method is used to create rigid heel cups or supportive inserts in the sole. Adidas employs several branding techniques for footwear. Thermal printing embeds logos and textured patterns into fabric or leather under high temperatures. Embossing creates raised logos on leather and synthetic components. Embroidery is used on textile models, such as the Stan Smith series. Reflective coatings enhance visibility in low light conditions. Right now, take a closer look at your sneakers and comment on which branding method was used on them. Cutting takes anywhere from several minutes to an hour, depending on model complexity and materials used. Component preparation, including lamination, heat treatment, and logo application, can take several hours to a full day, as some steps require drying or curing time. Can you believe how much time goes into something that seems so simple? Incredible. The entire process is automated, but key stages involve operators who monitor quality and make adjustments. Adidas is currently experimenting with three-dimensional printing of shoe components, which could revolutionize cutting processes. Laser cutting also enables the creation of complex ventilation holes in shoes without additional stitching. Using laminated materials improves waterproofing without increasing shoe weight. After completing all preparatory stages, the finished components move to the next critical phase, sewing and shoe assembly, where they begin to take their final shape. Sewing machines join individual shoe upper parts, ensuring durability and a polished aesthetic. Adidas production lines use specialized automated sewing machines that operate at high speed and run continuously for extended periods. These machines execute various stitch patterns with precision, ensuring both strength and clean seams. As materials pass through multi-step mechanisms, needles create perfectly aligned stitches that form even and neat seams, enhancing shoe durability and longevity. Once all upper shoe parts are combined into a unified structure, the machine completes the final touches, reinforcing stitches, securing details, and performing quality control. Every component is perfectly aligned and interconnected. As a result, nearly finished footwear emerges, transformed into a functional and stylish product through a blend of mechanical precision and human craftsmanship. Some models feature seamless technology to enhance comfort and reduce weight. Soles are formed by molding material under high pressure to achieve the required shape and properties. Once the upper shoe parts are stitched together, the next step is attaching them to the sole. High-quality adhesives are applied to specially prepared surfaces. These adhesives create a secure bond between components, preventing detachment during wear. Next, shoes pass through a conveyor system, where each pair enters specialized pressing machines. These machines use high pressure and temperature to tightly fuse the sole and upper, ensuring a strong bond. The conveyor smoothly moves each pair through multiple stages, from adhesive application to pressing, undergoing a series of heating and cooling cycles to finalize the adhesion process, making the shoes durable and ready for further stages. Every year, we produce approximately 101 million short tons of textile waste, and more than half of that trash simply rots in landfills. But what if we could turn it into something useful? Imagine this: your favorite t-shirt, a stylish blazer, or even designer sneakers, all made from plastic bottles. Yes, fashion is already changing, and brands are turning waste into trendy clothing. How exactly does plastic become fabric? Why are large companies already earning millions from this? And does such clothing truly save the environment? Let us figure it out. Every year around the world, approximately 101 million short tons of textile waste are produced, of which only 15% is recycled, while 57% ends up in landfills. We need to do something about that, right? It might sound like science fiction, but in fact, plastic can be easily recycled into fabric. Let us start with the fact that most of the textiles we wear every day consist of synthetic fibers, such as polyester. Here is something interesting. Polyester is nothing more than plastic. Yes, you understood that correctly. Plastic bottles or other plastic waste can be turned into fibers that are then used to make fabrics. The process looks like this. Old plastic bottles, plastic containers, or even damaged plastic items are collected, washed, cut into small pieces, and then these pieces are melted down into new plastic fibers. These fibers are then woven into fabric that, in terms of its characteristics, is almost no different from traditional materials like cotton or wool. Now imagine this. It is not just a technological marvel, but also a chance to reduce the amount of plastic that ends up in nature. This usually happens in the following way. Plastic is sorted by type of plastic, most frequently polyethylene terephthalate, and by color. Clean and transparent plastic is more valuable because it is easier to obtain high-quality raw material from it. After that, the waste is washed in special baths to remove any remaining beverages, glue, and labels. Then, special industrial shredders equipped with sharp blades cut the plastic into uniform fragments. Sometimes water cooling is used for this purpose, in order to avoid overheating the material. The smaller the plastic is shredded, the easier it is to melt and clean it from impurities. Next, the shredded plastic is heated to about 932 degrees Fahrenheit until it becomes a viscous liquid mass. Then, this melted mass goes through special filters to remove any remaining contaminants. After that, it is extruded through fine nozzles, creating thread-like fibers. These fibers are cooled by a stream of air or water, after which they are twisted into yarn that becomes the basis for textile materials. It is impossible not to notice that fashion is now moving towards sustainability. All those popular brands we know and love, such as Adidas, Patagonia, and Stella McCartney, are increasingly using recycled plastic in their collections. However, let us pause here. What makes this plastic so popular? Environmental friendliness. As we know, plastic is one of the biggest enemies of the environment. Every year, millions of short tons of plastic end up in landfills or in oceans. But through recycling, we can reduce that impact by turning plastic waste into useful materials. And this is not just one of the eco-initiatives of brands, it is a real shift in the industry. Interestingly, some designers and brands already use textiles made from recycled plastic, not only for environmental benefits, but also for the unique look. In particular, materials made of plastic fibers can have very intriguing texture and sheen, which gives clothing a bit of an innovative and futuristic appearance. Imagine a t-shirt that is not only made from plastic, but also has a striking texture that reminds us of the future. Research shows that reusing textiles can save up to 8 short tons of carbon dioxide and approximately 164 gigajoules of energy for every short ton of textile waste. Converting that to American measures, 164 gigajoules is about 155 million British thermal units. Recycling textiles saves 5 6/10 short tons of carbon and about 116 gigajoules of energy per short ton, which is around 110 million British thermal units. That is a considerable difference on a global scale. Technology. Fabrics made from recycled plastic can be just as comfortable and stylish as regular fabrics. They even have certain advantages. They are water repellent, resistant to fading, and they hold up well to wear and tear. Moreover, if these fabrics are processed correctly, they can be made soft and pleasant to the touch. And here, we should remember another point: microplastic that can enter water through recycled fabrics. When we wash clothes, especially items made from synthetic materials, microscopic plastic particles can get into the water. However, some brands are already working on solutions to minimize this impact. For example, they use special technologies to reduce the release of microplastic during washing, or they create materials that are less prone to this. Innovation. However, it is worth noting that this is not just a trend. It is an innovation. Instead of continuing to produce more plastic, brands are finding ways to use what already exists. This opens up new possibilities for the fashion industry. For instance, one of the most fascinating technologies is recycling ocean plastic. The same plastic that is flooding our oceans can also be turned into clothing. For example, the company Parley for the Oceans creates materials from plastic collected from the oceans. This not only helps decrease the amount of plastic in the water, but also becomes the foundation for eco-friendly collections by brands such as Adidas. That is a whole different story, right? If you think that recycled plastic is something only for sportswear or accessories, you are mistaken. Imagine a stylish coat or an elegant dress made from material that was once a plastic bottle. These recycled plastic fabrics make their way onto the runways of major fashion shows and become part of refined collections. One of the most interesting examples is the Stella McCartney collection, which recently introduced a clothing line made from fabrics produced from recycled plastic bottles. And of course, you will not find any trace that these fabrics were ever anything else. they look and feel completely sophisticated. This is not merely about disposal. It is about creating genuine art out of what we used to throw away. Speaking of scale, some countries, such as the Netherlands or Sweden, have become true leaders in plastic recycling. There are even specialized factories there that transform plastic waste into textile, which then becomes part of both sports and everyday clothing. It is an entirely new approach to waste processing that not only helps preserve resources, but also creates new jobs. It turns out that the process of recycling plastic into textile not only saves the planet, but also has significant economic potential. Many small startups around the world have begun to build business models based on the collection, recycling, and resale of plastic waste in the form of clothing. Such businesses often collaborate with local communities, involving them in collecting and recycling waste, which creates new jobs and stimulates the economy at a local level. Technologies of three-dimensional printing also use recycled plastic to create fabrics. Some companies have already started making textile materials by utilizing plastic waste through three-dimensional printing. This allows the creation of entirely new textures and shapes, as well as optimizing the clothing manufacturing process. Imagine clothing that is literally printed using plastic. In recent years, the so-called smart fabrics have also been gaining popularity in the textile industry. Materials that can change their properties depending on the surrounding conditions. Recycled plastic has a role here as well. Some brands are experimenting with integrating nanotechnologies into fabrics made from recycled plastic, enabling the creation of textiles that respond to temperature or moisture, making clothing more functional and comfortable. It sounds like something from a fantasy, but there are already materials made from recycled plastic that can self-clean. They have special coatings that allow the fabric to repel dirt and water. This technology can change the rules of the game in terms of durability and convenience, because clothing made of such fabrics would require much less washing. Another exciting direction involves fabrics that alter their appearance depending on how a person interacts with them. For example, fabrics that respond to body heat or change color during movement. All of these innovations can be created using recycled plastic, opening up new opportunities in fashion. One more interesting aspect is the recycling of plastic into artificial leather. Some innovative brands have already started making eco-friendly artificial leather out of recycled plastic waste. Such leather can be used to manufacture bags, footwear, and even outerwear. This offers a material that resembles genuine leather, but without the use of animal products and with a smaller environmental impact. Here is the thing. Today's youth is a generation that is becoming increasingly aware of environmental issues. You are no longer just buying clothing. You are buying clothing that tells a story. You are buying not just fabric, but a certain idea. A future that can be more sustainable and clean. And when you wear clothing made from recycled plastic, you are not merely shopping. You are joining the change. You are becoming a part of this large movement. Of course, there are questions about the cost, quality, and availability of such materials. But do you know what? It is only a matter of time. With the advancement of technology and the growth in demand for eco-friendly products, these fabrics will become even more affordable. And that is great, because each of us can contribute to improving the situation. Perhaps in a few years, we will only wear clothing made from recycled material. And, to be honest, that does not seem so fantastic. It might become the norm, rather than the exception. And who knows, maybe in the future, even your favorite brand will use plastic waste to create new trendy items. Yes, it sounds like science, but science and fashion can accomplish many wonders together. So the next time you are choosing what to wear, think about this. Maybe it is another step toward a better world. And if plastic waste can become part of your style, then why not? Every single day, more than 15 billion cigarettes are produced worldwide. That is 173,000 every single second. But how does an ordinary tobacco leaf transform into a cigarette? What happens behind the closed doors of factories, where massive machines work non-stop to roll out thousands of packs every single hour? Today, we will reveal all the secrets, from enormous tobacco plantations to high-tech packaging lines. And you will be shocked at the hidden processes behind this industry. Stick around until the end so you do not miss the most fascinating details. The very first tobacco factory in Europe was established in Seville, Spain, in the year 1728. For over a century, this factory supplied Europe with cigars, generating substantial profits for the Spanish treasury. Today, Europe is home to major tobacco companies such as British American Tobacco, Philip Morris International, and Imperial Brands. For instance, in the year 2024, Imperial Brands reported an operating profit of £3.5 billion British pounds, which was 4.5% higher than the previous year. This growth was driven by a 26% increase in revenue from alternative products, such as electronic cigarettes and nicotine pouches. Growing tobacco requires a specific climate, as this plant thrives in warm weather and fertile soil. The primary regions for tobacco cultivation include North and South America, Africa, Southeast Asia, and Europe. The leading countries in tobacco production are Brazil, China, India, the United States of America, Zimbabwe, Turkey, and Italy. China is the world's top tobacco producer, cultivating more than 2 million metric tons of tobacco leaves annually, which accounts for over 40% of global production. The key tobacco growing regions in China are Yunnan, Guizhou, Hunan, and Sichuan provinces. India produces approximately 800,000 metric tons of tobacco per year, primarily in the states of Andhra Pradesh, Telangana, and Karnataka. Tobacco seeds are sown in the spring, and the leaves are harvested several months later. This process can take several weeks since each layer of leaves is collected separately. After harvesting, the leaves are transported to specialized facilities, where they undergo fermentation and drying. The most common drying methods include air curing, fire curing, or sun curing, depending on the type of tobacco. For instance, Virginia tobacco is fire cured, meaning the leaves are hung in curing barns where the temperature is carefully maintained using heated air. This process lasts about 7 to 10 days and gives the leaves a golden color and a mildly sweet aroma. Burley tobacco, on the other hand, is air cured in shaded barns for an entire month, resulting in a more intense and dry flavor. After drying, the tobacco leaves go through fermentation, which helps reduce nicotine levels and remove excessive bitterness. This fermentation process can last several months. A large portion of the tobacco used for cigarette production in Europe is imported from Brazil, Zimbabwe, China, and the United States of America. Some countries, such as Italy, Greece, and Turkey, cultivate their own tobacco, which is also processed in local factories. Every batch of tobacco arriving at production facilities undergoes strict quality control, where factors like moisture content, color, and nicotine levels are analyzed. The process begins with the initial treatment of tobacco leaves. First, the leaves are sorted by quality and type, with damaged or unsuitable parts removed. On average, each cigarette contains approximately 1 gram of tobacco, meaning that large factories process hundreds of metric tons of raw materials daily. After sorting, the tobacco is processed in manufacturing plants, where machines take over most of the work. The leaves are first shredded into fine fibers. Machines meticulously control the size of these shredded pieces to ensure uniformity. Then, the tobacco undergoes steam treatment to increase its elasticity and improve storage conditions. Various flavorings and stabilizing agents are added to regulate moisture levels and enhance taste characteristics. Typically, cigarette blends include a mix of different tobacco varieties to achieve the desired flavor and strength. The next stage is cigarette formation. Production lines are equipped with specialized machines capable of rolling out more than 20,000 cigarettes per minute. These automated lines operate with incredible speed and precision. The process begins with shredded tobacco being evenly distributed onto a conveyor belt. Next to this belt, a continuous strip of cigarette paper is unrolled. The machine wraps the tobacco in the paper, forming an uninterrupted tube that resembles a long roll. This roll moves along the belt at high speed, and special cutting blades then slice it into individual cigarettes, each approximately 3 inches long. Filter production is a separate process that begins with a primary material, usually acetate fiber. This synthetic polymer is derived from cellulose, which comes from wood pulp. The fibers are treated with special chemicals to give them the required structure, after which they are pressed and formed into long strips. To bind the fibers, a plasticizer called triacetin is used, ensuring the filter maintains its shape. These long strips are rolled into cylindrical blanks, which can be several feet long. They are then cut into smaller sections that match the required filter length. On the production line, these filters are fed into a specialized mechanism that wraps them in a thin paper layer to reinforce their structure. A standard filter can weigh between 10 and 20 grams, depending on the type, and its volume can range from 1 to 3 milliliters. In large-scale manufacturing, several metric tons of acetate fiber may be processed daily, with the total volume of filters produced reaching hundreds of thousands of liters. Next, the filters are attached to the tobacco rod. This is done using wrapping paper that is bonded with food-grade adhesive to create a strong connection between the filter and the tobacco-filled portion. In the bonding area, the wrapping paper passes through a roller that evenly applies the adhesive to its surface. The filter and the tobacco rod are then precisely aligned and merged using a specialized mechanism. The wrapping paper is tightly wound around the connection point and firmly pressed to ensure a secure bond. This process happens in a fraction of a second, and each minute, the machine can attach hundreds of filters to tobacco rods. Throughout production, the total amount of adhesive used can reach several dozen kilograms per shift, while the length of tobacco rods passing through the equipment is measured in hundreds of yards. Once assembled, the cigarettes move along the conveyor to the inspection section, where the strength of the bonds, uniformity of the wrapping, and adherence to standard dimensions are checked. Special scanners and weight sensors examine each cigarette to detect any defects, such as hollow spots, uneven tobacco distribution, or damaged paper. Any defective items are automatically removed from the line. Another crucial step is the application of tracking codes on each cigarette or filter, ensuring full traceability throughout the production cycle. This is done with high-precision laser markers that do not damage the paper. Finished products are then cut to final lengths if needed before reaching the packaging section, where they are grouped into packs of 20 and wrapped in foil. Once cigarettes are paired with filters and pass quality control, they move to the packaging stage. First, the cigarettes are aligned on the conveyor, forming groups based on the intended pack size. A standard pack typically contains 20 cigarettes, although there are variations with 10 or 25 pieces. Once grouped, the cigarettes are wrapped in an inner lining made of foil paper or thin aluminum foil to maintain freshness and prevent drying. They are then automatically placed into cardboard boxes, which arrive via a separate conveyor. These boxes are made from thick cardboard that is pre-cut, folded, and glued using high-speed machinery. The packs then pass through a wrapping mechanism, which seals them in a thin, transparent film. This film includes a perforated strip for easy opening. At this stage, excise stamps and barcodes are printed. On average, a single packaging line can process about 15,000 packs per hour. Completed packs are arranged into blocks of multiple packs, usually 10 per block. These blocks are further wrapped in film or packed into cardboard boxes before being placed onto pallets for transportation. Large cartons can hold up to 500 packs each. The boxed products are stored in factory warehouses until they are shipped to distributor warehouses. From there, cigarettes are sent to stores, supermarkets, and specialized kiosks. Every day, dozens of trucks leave major tobacco factories, delivering millions of cigarettes to distributors and retail locations. The entire journey, from manufacturing to store shelves, can take anywhere from a few days to several weeks, depending on logistics and market demand. At large tobacco factories, machines operate continuously across multiple shifts. In a single workday, one of these machines can produce several million cigarettes. Modern cigarette manufacturing is characterized by a high level of automation, minimal human involvement in production, and rigorous quality control at every stage. Factories are equipped with air quality management systems to maintain stable humidity and temperature, which are crucial for preserving tobacco properties. A typical tobacco factory can produce up to 200 million cigarettes per day, amounting to thousands of metric tons of finished products each month. This is one of the most expensive and complex machines ever built by humankind. Constructing it costs more than $3 billion and takes over 7 years to complete. It can dive to depths of more than 3,000 feet, remain submerged for months without surfacing, and launch missiles capable of altering the course of war. But how exactly is a nuclear submarine? An engineering masterpiece that remains nearly invisible even to the most advanced radars, built. Right now, you are about to witness this incredible process. A nuclear submarine is a highly sophisticated engineering marvel, and its creation begins long before the first sheet of metal ever touches the manufacturing tools. The initial designs are developed using advanced computer modeling software. At this stage, several critical parameters are considered, including hull dimensions and shape, power systems, weaponry, and noise reduction technologies. The length can range from 300 to 550 feet, directly impacting the submarine's diving depth based on its class. The most advanced submarines can descend to depths of 2,000 or even 2,500 feet, while some experimental models can go beyond 3,000 feet. Based on these initial designs, physical models of the submarine are constructed and tested in water tunnels. This allows engineers to analyze how the hull shape affects maneuverability, water resistance, and noise levels. Meanwhile, computer simulations help predict the submarine's behavior underwater at different speeds and during various maneuvers. Once all simulations confirm the calculations, the blueprints are sent to production. This is where theory turns into practice. Building nuclear submarines requires special materials capable of withstanding extreme pressure at great depths while providing corrosion resistance. Typically, high-grade steel or titanium alloys are used. Steel is more cost-effective and easier to manufacture, as it can endure high pressure and impacts. Titanium, on the other hand, offers superior strength, corrosion resistance, and non-magnetic properties, which reduce the risk of detection. However, titanium is more challenging to process and weld, as its melting point is significantly higher, approximately 3,034 degrees Fahrenheit, compared to steel's 2,500 degrees Fahrenheit. Before construction begins, all metal sheets undergo heat treatment, which involves heating, cooling, and applying special anti-corrosion coatings. The hull of a modern submarine is assembled from modular sections, simplifying the construction process. Metal sheets are cut with massive laser and plasma cutters, ensuring precision down to the millimeter. Each sheet is then shaped using hydraulic presses to achieve the desired curvature. Some parts of the hull feature spherical or cylindrical structures. The sections are assembled separately. These are massive rings, or compartments, that will be joined in the final stage. This modular approach allows different sections of the submarine to be worked on simultaneously, accelerating the overall construction timeline. Once all components are ready, the most critical phase begins: welding the hull. Welded seams must be exceptionally strong, as even a microscopic crack could lead to catastrophe at great depths. To meet all safety standards, automated electron beam welding is used, producing perfectly uniform seams. Additionally, every weld is inspected using ultrasonic scanners and X-rays. Most nuclear submarines feature a double hull design. The strong inner hull withstands deep sea pressure, while the outer hull provides a streamlined shape, improving hydrodynamics and reducing detectability. Ballast tanks are often located between these hulls, allowing for buoyancy control. To keep the submarine as stealthy as possible, anti-sonar coatings are applied. These include noise-dampening polymer tiles that absorb sound waves, microporous composite materials that minimize the submarine's acoustic signature, and noise-reducing coatings for the propellers and power systems. Once all sections are ready, they are connected. Gigantic cranes transport the compartments into specialized docks, where they are bolted and welded together. The completed hull is then tested for air tightness by filling it with compressed air and checking for leaks. A structural integrity test is also conducted in a hydrostatic pressure chamber, simulating real deep-sea conditions. Once the submarine's hull is assembled and its strength verified, it is time to install its most crucial component, the nuclear reactor. This is the heart of the submarine, allowing it to stay submerged for months, or in some cases, even years. A nuclear reactor is more than just a machine. It is an entire energy system consisting of various auxiliary components that occupy a significant portion of the submarine. Modern nuclear submarines use reactors that function by heating water to generate steam. The nuclear fuel, typically enriched uranium-235 or uranium-238, is placed inside the reactor's core. As nuclear reactions occur, heat is produced, which then heats water in a closed-loop system. The resulting steam drives turbines that generate electricity and power the propeller. The reactor is transported in protective containers and installed using cranes through a designated hatch on the upper part of the hull. It is placed within a specialized compartment in the submarine's core, surrounded by radiation-blocking materials. This compartment is also equipped with emergency cooling systems and reinforced safety barriers. The reactor is mounted on a shock-absorbing platform that minimizes vibrations and impacts during submarine movement. Next, heat exchangers and steam generators are installed to ensure efficient coolant circulation, followed by the installation of turbines and electric generators, critical components for the submarine's overall operation. Finally, the compartment is sealed with multi-layered lead and composite panels to minimize radiation exposure to the crew. To ensure functionality, an initial test ignition of the reactor is performed. During this test, power levels are gradually increased, radiation levels in all compartments are measured, and cooling systems are tested under maximum loads. With the reactor in place, the submarine is still far from operational. At this point, it consists of empty corridors and compartments, so the next step involves installing control systems, life support mechanisms, weaponry, and crew quarters. Sonar systems are mounted in the bow and along the hull, enabling the detection of enemy vessels and underwater terrain mapping. The onboard computer system and automated combat control stations are integrated, ensuring precise maneuvering capabilities. Weapon systems are also installed. Torpedo tubes are positioned at the front, equipped with automated reload mechanisms for rapid firing. Strategic submarines are fitted with missile launch silos located in the central hull. Each silo is equipped with hydraulic locks and pressure control systems, allowing for missile launches at extreme depths. Considering that the crew can remain submerged for months without surfacing, nuclear submarines must be self-sufficient. They are equipped with oxygen generators, carbon dioxide removal systems, heating and ventilation mechanisms, and water reserves. Ever seen those tiny capsule hotels? Well, submarines have something very similar: sleeping capsules. They also feature dining areas stocked with provisions and a command center filled with control panels, maps, and communication devices. After the living quarters are fully equipped, the submarine is almost ready for deployment. But the most thrilling phase remains: a series of rigorous tests to prove that it can withstand immense pressure, stay undetectable, maneuver in extreme conditions, and perform combat missions. These tests can last anywhere from 6 months to 2 years, and include both factory trials and combat training for the crew. The submarine undergoes another airtightness test, followed by assessments of its electrical and navigation systems, and a final reactor ignition. For the first time, the submarine leaves the shipyard and enters open waters. Stabilizers, hydraulic cylinders, and steering mechanisms are tested. Sharp turns, dives, emergency maneuvers, and maximum speed tests, typically 25 or 35 knots, are performed. The submarine then submerges to periscope depth, about 65 feet, to evaluate stability. At greater depths, ballast tanks are tested under load, and the submarine is gradually lowered to its maximum allowable depth, usually around 2,000 feet, depending on its class. Reactor performance under maximum load is also assessed. Once the submarine has proven its seaworthiness, combat systems are tested. Initial shots are fired using training torpedoes without warheads. Strategic submarines conduct the launch of a single ballistic missile, typically following a launch-dive-airburst trajectory. Tactical submarines perform test launches of Tomahawk missiles or similar weapons. The submarine also enters an area with hydroacoustic sensors, where specialists measure noise levels at various speeds and evaluate the effectiveness of its sound-absorbing rubber coating. Finally, the submarine undergoes a simulated combat mission, during which the crew must demonstrate full operational readiness. Every year, more than 22,000 short tons of amethyst are mined all over the world. But how do these unique purple crystals end up on display in jewelry stores? Picture enormous geodes, each roughly the size of a person, packed with dazzling crystals that miners extract from remote regions in Brazil, Uruguay, and Africa. Some of these geodes are so rare that they are transported by helicopters. However, did you know that only about 10% of all discovered amethysts are of jewelry quality? Let us dive into a world where nature creates masterpieces and humankind unveils them for everyone to see. Brazil is one of the largest suppliers of amethyst on the planet. The main deposits are located in the states of Rio Grande do Sul and Minas Gerais. In Brazil, amethyst geodes are often found, which are hollow stone formations lined with crystals on the inside. Some geodes can reach over 9 feet in height. Uruguay is famous for its amethyst that has a rich, dark purple hue. This stone is usually of higher quality than the Brazilian variety. Geodes from Uruguay are considered extremely valuable because of their depth of color. The African continent, particularly Zambia, is also an important source of amethyst. Zambian amethysts feature a unique purple color with a bluish tint. They are mined in considerable volume, but the deposits are located in hard-to-reach regions, making transportation more complicated. Amethyst deposits in the United States are not as large-scale as in Brazil or Uruguay, but they have their own special history and appeal. The amethyst found in the United States is prized for its vibrant coloring, historical significance, and local popularity. So, let us take a closer look at the main locations and their distinctive features. Four Peaks is the most renowned and likely the largest amethyst deposit in the United States, situated in Arizona, at an elevation of about 7,545 feet above sea level. The amethyst from Four Peaks is noted for its deep purple color with a subtle reddish glow. Many believe these stones can compete in quality with even the most valuable specimens from Uruguay. The deposit is located in an extremely challenging spot. There are no roads, so miners and equipment are transported by helicopters or on mules. This is one reason why stones from this deposit are so expensive. The mining process is physically demanding and costly. Most of these mines are small, and much of the work is done manually to avoid damaging the crystals. A modest region in the northern part of Georgia is home to lighter, pastel-toned amethysts. Although the deposits are not as extensive as those in Arizona, the stones exhibit a unique clarity and a pleasant purple hue suitable for more affordable jewelry. Local specimens are often mined in small private shafts or even during special tours that allow tourists to try their hand at being treasure hunters. This aspect adds a certain charm to Georgia amethysts, as they become both a souvenir and a cherished memory. The Creede area in Colorado was once more famous for its silver mines. However, there are certain spots where amethyst deposits can be found as well. These stones tend to be lighter in color and less intense in saturation, yet they possess interesting inclusions that give them a unique character. Amethysts from Creede are frequently used to make cabochons, which are smooth, unfacetted stones suited for decorative ornaments. Amethyst usually forms in volcanic rocks, where high temperature and pressure conditions cause quartz to absorb iron impurities, then cool over thousands of years. The outcome is a deep purple crystal that makes you pause and exclaim, "Wow!" For example, in Brazil, miners uncover enormous geodes lined with crystals. Sometimes these geodes are so large that they appear at exhibitions, where people take photos beside them, as if they were standing next to a work of art. Now imagine this scene: a team of miners wearing hard hats, equipped with headlamps and pickaxes, searching for just the right pockets of stone where these priceless cocoons lie hidden. Believe me, it is no simple task. Today, miners do not rely solely on luck in their pursuit of amethyst. Their primary allies these days are science and technology. The process starts with detailed geological mapping. Geologists investigate regions that are well known for containing abundant quartz, the primary mineral from which amethyst arises. For instance, in Brazil, the world's largest amethyst producer, researchers target geological formations ranging in age from 50 million years to 200 million years. One of the most advanced tools is high-resolution satellite imagery. Through spectral analysis of the colors on the Earth's surface, specialists can pinpoint hues that hint at the presence of specific minerals, including quartz. Moreover, seismic sensors contribute to the creation of three-dimensional models of the underground layers of soil. These devices detect even minute reflected waves that tell the story of the materials hidden below the surface. Yet, as strange as it may sound, intuition and hands-on experience still play a huge role. For instance, miners in Rio Grande do Sul in Brazil claim that deep reddish-brown soil nearly always indicates proximity to amethyst. Such observations help them concentrate their efforts exactly where the odds of discovering stones are the greatest. Statistics show that only about 5 to 10% of all areas that look promising based on maps or satellite data actually harbor commercially valuable deposits. In Brazil, which accounts for over 40% of the global amethyst market, dozens of new zones are surveyed every year, but only a handful proceed to the extraction phase. The average depth of an amethyst mining site seldom exceeds a few dozen feet, but these locations demand enormous amounts of preliminary work. According to the United States Bureau of Mines, launching a single mine may require as long as 3 years and cost anywhere from $50,000 to $100,000 before unearthing even a small pocket of amethyst. This illustrates how labor-intensive and expensive the quest can be, even for gems as popular as amethyst. Ultimately, technology, expertise, and a hint of intuition collaborate to uncover those mysterious purple treasures that we admire in jewelry. Although the probability of finding the ideal crystal is slim, and the miner's work is strenuous, the reward is unquestionably worthwhile. The amethyst extracted from a mine looks nothing like what you see in a display case. It is often covered in rocky residue, irregular in shape, sometimes almost opaque. Once it is mined, the stone goes to a factory, where a kind of magical transformation unfolds. First, the crystals are cleaned, occasionally by hand, and occasionally in massive tumblers that literally scrub away the dirt. Then each stone is sorted by quality. Here is the interesting part. Only about 10% of all the amethysts unearthed are of jewelry-grade quality. The rest are used for more budget-friendly accessories or even ornamental items. The next step is cutting. This is a true art that merges careful science with the delicate touch of a skilled artisan. Picture a person peering through a loop, meticulously turning the stone to find the ideal angle. The most fascinating aspect? One slip of the hand can cause the crystal to crack. Let us suppose the stone is finished. The next issue is transportation. This task is not as straightforward as one might initially assume. Certain amethysts travel in specialized boxes, padded with foam inserts to protect them from the faintest jostles. In the case of geodes, they are often packed in wooden crates lined with soft materials. Uruguay has a distinctive export program for its amethysts. Stones are sold directly at auctions, drawing buyers from all over the globe. In Brazil, on the other hand, most of the output goes straight to large enterprises that handle both cutting and further distribution. The price of amethyst is determined by factors like color, clarity, and size. The most expensive pieces boast a vivid purple tone with a slight reddish shimmer, often called deep royal. Such stones are frequently utilized in luxurious jewelry, which can appear at international auctions. Here is something surprising. Even though technology has improved remarkably, a great deal in this field still hinges on human effort and observation. It is a tradition passed down through many generations. Even the extraction itself relies more on manual labor than on large machinery. Initially, after identifying a promising zone, preliminary work begins. If the amethyst is near the surface, excavators remove the topsoil, creating large open pits. In places like Minas Gerais and Bahia in Brazil, these open pits can span several dozen feet across. However, if the amethyst is buried deep, the operation goes underground. Mines that yield this crystal can extend about 320 feet into the earth, forming a vast maze of tunnels branching out in all directions. Breaking through the tough layers of rock is the first step to reaching amethyst. This may involve using explosives or drill rigs, but it is not as dramatic as one might imagine. It must be done very carefully to avoid shattering the precious crystals. The people responsible for this work are genuine experts. They even live by an informal motto: "It is better to go around than to destroy." A carelessly managed blast can reduce a stone to fragments. Once the deposit is exposed, miners proceed by hand or with small tools to gently dislodge the crystals. Envision the scene: darkness, illuminated only by the glow of headlamps, and silence broken by the occasional strike of a pickaxe or the hum of a handheld saw. Everything relies on the miner's dexterity. Even the most subtle motion can determine whether a crystal remains intact or breaks. Some refer to this phase as jewelry-level work. The amethysts that are found are typically surrounded by quartz, rock, and clay, so they are cleaned right there in the mine. This is painstaking work, removing layer after layer and taking care not to harm the delicate crystal structure. It is reminiscent of restoring an antique vase. The most valuable crystals are separated by hand, with every movement carefully planned. Interestingly, the ambience in these mines can be quite a spectacle. For example, in the famous Las Vegas mine in Uruguay, amethysts shimmer in the darkness under the beam of a lamp, creating the sense of stepping into a magical subterranean realm, radiating shades of purple and blue. In some locations, such as the Amethyst Park in Brazil, the mines are open to visitors, and people can witness firsthand how skilled workers gently extract the crystals from the walls. Those workers are the real heroes. They toil in challenging conditions. Do you know what can amaze you even more than the flight of an airplane itself? It's life after the sky. Every year, thousands of airplanes are retired worldwide, and some of them become a source of metal for new automobiles or even construction frameworks. One single Boeing 747 contains around 165,000 pounds of aluminum, which can become the future raw material for dozens of other airplanes. Are you curious to learn how engines, which can cost up to $30 million, get a second lease on life? Or how first-class seats turn into part of a home movie theater setup? Are you ready to journey into a realm where technology, ecology, and business converge in one enormous hangar? Let us take off and explore. The first step in a retired airplane's journey is what insiders often call its removal from flight. In fact, this phase is sometimes referred to rather poetically as heading into retirement. Airplanes are retired when they reach a certain age, a certain number of flights, a certain tally of hours in the air, or when they simply become economically unviable to operate. Passenger airplanes typically serve from about 20 years to about 30 years. The metal gradually becomes fatigued from the repeated cycles of takeoff and landing, alongside the persistent air pressure at cruising altitudes. Engineers may detect microcracks or other structural issues, making further flights risky. Older airplanes require more frequent maintenance, which becomes expensive. Eventually, the costs of upkeep can overshadow any profit from keeping that aircraft in service. More modern airplanes consume less fuel, are cleaner for the environment, and cost less to operate. For instance, contemporary designs, such as the Boeing 787 or the Airbus A350, are far more efficient than older airplanes like the Boeing 747. International safety standards also keep shifting. If an airplane does not meet new standards and modifications prove too pricey, that airplane is retired. Occasionally, airlines retire airplanes because travel demand declines. During the coronavirus disease 19 pandemic, many older airplanes were retired ahead of their original timelines. Interestingly enough, cargo airplanes can keep flying for a longer period, as there are fewer requirements for passenger comfort, and their overall load can be lighter. Yet sooner or later, even cargo airplanes head into retirement. Once an airplane is ready for disassembly, it is towed to a specialized hangar, where its second chapter really begins. The first priority is the engines. They are, beyond any doubt, the most valuable part. Engineers remove them first, perform detailed inspections, and then either overhaul them for reuse or break them down for spare parts. One of the staff members told me that a single engine can be more expensive than the entire airplane. Can you imagine that? The process starts with engineers reviewing the documentation for both the airplane and the engine. They want to know its overall condition, its servicing history, and whether any special precautions are needed. All fuel, hydraulic fluid, and lubrication systems in the engine are de-energized, with every liquid drained. This step is crucial, since even small amounts of leftover fuel or oil can be a fire hazard. The engine is linked to the airplane by dozens of cables, pipes, and mechanical connections. One at a time, engineers disconnect the electronics, hydraulic lines, and ventilation and cooling systems. All connectors are labeled so that they can be quickly identified whenever the engine is inspected or installed on a different airplane. The cowling is the protective shell around the engine. It is taken off to reach the main components underneath. This cowling is removed very carefully and often sent away on its own for inspection or repair. Engines can weigh several thousand pounds, so they must be firmly supported before removal. Specialized lifting platforms or cranes are used to ensure the engine remains undamaged during detachment. Engines are attached to the wing or fuselage by pylons, which are special mounting structures. Engineers gradually remove these attachments, frequently by hand, using high-precision tools. It is a delicate moment, since a slip can cause damage. Following removal, the engine travels to a service facility for inspection, repairs, or further disassembly. It is secured in a dedicated container that safeguards every part during transport. The engine is the priciest piece of the airplane. Depending on the particular model, it may cost anywhere between $10 million and $30 million. As a result, the removal process is carried out with extreme caution. Often, an engine is not taken off because of a failure, but rather to undergo planned maintenance, or so it can be installed on another airplane. In many cases, engines embark on a new life after refurbishment and upgrades. This underscores yet again that aviation is not just about flying, but also about pragmatic reuse and a certain technological artistry. The next thing that amazed me was the fuselage. The aluminum body of an airplane is not simply chopped into random pieces. Instead, it is sorted, cleaned, and directed toward recycling. This metal can be reborn as part of new airplanes, car parts, or even building materials. By the way, have you ever wondered how much aluminum is inside a single Boeing 747? It is about 165,000 pounds, which is impressive to envision. That quantity could practically spawn an entire fleet of future airplanes. Seats, which we usually see as nothing more than comfortable chairs for our flight, can also be reincarnated. They are repaired and sold to airlines that have tighter budgets. Sometimes they even end up with private buyers. Did you know that first-class seats can be purchased for a home movie theater? That idea is definitely on my personal wish list. Aviation electronics form another treasure trove. Every component, from onboard computers to navigation systems, is extracted and carefully evaluated. These parts often see further use in pilot training simulators or get integrated into other airplanes. Even seemingly small items, such as life vests, seatbelts, or tableware, find new owners. Some of them are turned into unique souvenirs. Do you recall those movies in which people collect aviation memorabilia? That is actually based on reality. Aviation collecting can be quite costly. For instance, the nose section of an airplane or an antique propeller can sell for thousands of dollars. If a piece is historically significant, say it comes from an airplane involved in the Second World War, its value could multiply dramatically. The aspect that left me most astonished was the team's flawless coordination. They moved as if they were dismantling a gigantic construction set, with each part assigned its own special place in the bigger picture. It was almost like a dance involving both machinery and people, all working in harmony to accomplish something meaningful. Think about it. A single airplane can yield up to 50,000 parts. Someone has to track each nut, each bolt, and each panel, making sure everything lands in the right container. Logistics teams then see to it that no part gets lost and that every component reaches its intended destination, whether it is a repair center or a recycling facility. Disassembling an airplane is definitely not a matter of taking it apart and forgetting about it. Proper disposal protocols must be followed for all hazardous substances, such as unused fuel, hydraulic fluids, and batteries. Environmental teams and safety inspectors ensure that every step complies with regulations and safeguards the planet. Having witnessed all this, I am convinced that aviation is so much more than just flying. It is about ecology, business, and even a touch of art. Now, whenever I look up and see an airplane cutting across the sky, I find myself wondering what the future holds for it. How about you? So the next time you watch an airplane soar overhead, remember that even after its final flight, it can transform into something far greater. Did you know that over 2 billion cups of coffee are consumed every single day around the world? But how does your morning drink begin its journey from a tiny coffee cherry? Today, we're uncovering the secrets of instant coffee. From the first blossoms of coffee trees to the cutting-edge factories where beans transform into aromatic powder. Why is Arabica so delicate and Robusta so hardy? And how does production involve technologies that seem straight out of a sci-fi lab? Stick around. You'll be amazed by how many hands and minds it takes to create every jar of coffee. Before beans make it to the factory, they travel a long way, from small coffee plantations to industrial mills, and this journey starts long before the beans are ready to work. First, let's talk about Robusta and Arabica. They're like totally different personalities. They grow in different conditions, offer distinct flavors, and have unique growing demands. Fun fact: instant coffee usually uses Robusta, a bean known for its strength and high caffeine content. Arabica is also used, but less frequently, mainly in premium blends to add a smooth, sweeter flavor. Arabica is the premium bean. It's grown high up in the mountains, typically at elevations of 800 to 2,000 feet above sea level. It's picky. It loves mild climates, consistent rainfall, and temperatures between 60 and 75 degrees Fahrenheit. Robusta is less fussy. It thrives in lowlands, can handle heat, humidity, and even pests. Its ideal growing temperature can reach up to 86 degrees Fahrenheit. It's often cultivated in tough climates where Arabica wouldn't survive. Coffee plantations look like small forests. Coffee trees are grown from seeds, and get this, they take up to 3 years to bear their first fruit. Yep, 3 years before those cherries, which aren't even the coffee beans yet, but their outer shells appear. The trees are planted on specially prepared terraces, especially Arabica on slopes. The soil needs to be loose, rich in minerals, and moisture balanced. On many plantations, work is still done by hand, though some larger farms now use machines for planting. Coffee cherries take about 9 months to ripen after the trees bloom. And here's where the magic begins, timing the harvest just right. Handpicking is the best and most precise method. Workers pick only the ripe cherries, leaving the green ones to mature. It's labor-intensive, but guarantees quality, especially for Arabica. Robusta is often harvested with machines that comb cherries off the trees. It's faster and cheaper, but ripe and unripe cherries end up mixed. Handpicking Arabica ensures better quality, but requires a massive workforce. Entire villages or even seasonal workers from nearby regions often help on large plantations. Harvested cherries aren't beans yet, they're just the shells. To extract the coffee beans, cherries undergo processing. There are 2 main methods: wet processing and dry processing. Wet processing is mostly used for Arabica. Cherries are soaked in water, where the pulp dissolves and the beans separate. It's pricier, but results in a clean, delicate flavor. Dry processing is more common for Robusta. Cherries are simply spread out to dry under the sun, and then the shells are removed. It's cheaper, but creates a bolder, more intense taste. After processing, the beans are sorted by size, weight, and quality. The best beans go into premium coffee products, while smaller or slightly damaged ones are used for more budget-friendly options or instant coffee. Here's something cool I learned. Robusta beans are usually round and tougher, while Arabica beans are oval and a bit softer to the touch. Once beans are ready, they're packed in classic jute bags. Why jute? It lets the beans breathe during transportation. On plantations, these bags are often loaded onto small trucks or even motorcycles to reach nearby ports or warehouses. Then, the beans are shipped in large containers that can carry hundreds of tons of coffee at a time. Beans often pass through several countries before reaching the factory. For example, coffee might be grown in Vietnam, one of the world's largest Robusta producers, processed in another country, and roasted or turned into instant coffee at a factory in Europe or the US. Before beans are transformed into instant coffee, they're checked for quality multiple times. On plantations, defective cherries are removed before processing. Before shipping, beans undergo another round of checks at warehouses and ports. This includes examining size, color, and aroma. At the factory, samples from each batch are tasted to ensure the flavor meets standards. Everything starts with coffee beans. At the factory I visited, roasted beans are delivered, and their smell, wow! It's that rich aroma you get when you walk into a coffee shop. Fun fact, roasting follows an incredibly precise schedule. Every second impacts the final flavor. So, where does roasting happen? At roasting facilities. Roasting is a whole universe of its own. It significantly affects coffee's taste and aroma, so it's taken seriously. There are several ways this can go down. Sometimes, especially for large Robusta volumes, beans are roasted in their country of origin, like Vietnam or Brazil. These countries have massive export-focused factories, which cut down on logistics costs. Big brands have their own roasting facilities in key regions. For example, in Europe or the US, there are giant factories specializing exclusively in roasting. Roasting beans separately isn't just a preference, it's logical. Green coffee beans are easier to transport long distances because they're less sensitive to storage conditions. Specialized facilities ensure a consistent roast level needed for specific products. Plus, depending on the end use, instant coffee or ground coffee, beans are roasted differently. Roasting coffee is a science. Beans are heated in rotating drums at temperatures around 400 degrees Fahrenheit. The roast time depends on the desired profile, lighter for softer flavors, darker for bold, intense notes. Instant coffee typically uses dark roasts. This enhances aroma and adds a bitterness that holds up even after processing. Roasted beans are cooled and packed to preserve their aroma. The factory receives this semi-finished product and focuses on its processes. It's a bit like a chef starting with a ready-made base to create a masterpiece. The first step after delivery is grinding the beans to a dust-like consistency. No, this isn't your regular grind for a French press or espresso. Industrial mills turn beans into particles finer than sand grains. Why so fine? I asked one of the staff. The answer was simple. The smaller the particles, the more efficiently the flavor and aroma are extracted in the next steps. Here's where the real chemistry begins. The ground powder goes into special extraction chambers, where it's brewed with hot water under pressure. Think of it as a giant coffee maker. This is where all the flavor and aroma you enjoy in your instant coffee are drawn out. What surprised me? The water temperature is controlled to the exact degree to avoid overbrewing. If it's too hot, the taste becomes bitter. Too cool, and the coffee loses its richness. The extract from these chambers undergoes multi-stage filtration. All unwanted particles are removed, leaving only a liquid concentrate. This concentrate looks like thick syrup and has such a strong aroma, it'll make your head spin. Next comes the most fascinating part. The liquid concentrate is turned into powder or granules using two main methods: spray drying or freeze drying. Spray drying involves blasting hot air to dry droplets of concentrate, leaving behind dry powder. It's fast and relatively cheap, but sometimes loses some aroma. Freeze drying is more complex. The concentrate is first frozen to extremely low temperatures, then sublimated, turning ice into vapor and leaving dry granules behind. It's pricier, but preserves maximum flavor. At the factory I visited, both methods were used depending on the coffee type. For premium lines, only freeze drying was used. The finished powder or granules are packed into jars, sachets, or sticks. It's all automated. Machines measure exact amounts, seal the packages, and add protective valves to preserve aroma. By the way, these valves are a real technological breakthrough. They let air out of the jar, but don't let it back in. You might wonder, how do they keep the aroma? The secret is that some of the coffee oils and aromatic compounds lost during extraction are collected separately and added back to the final product. It's like a little bonus that makes instant coffee so familiar and fragrant. Is instant coffee real coffee? You know, I was a bit skeptical myself until I saw the whole process. It really is 100% coffee, just with a touch of engineering magic. Actually, scratch that, it's more like technical mastery. The difference between instant coffee and freshly brewed coffee is like the difference between homemade pizza and takeout pizza. They're both great, but in different ways. Instant coffee is quicker, more convenient, and still incredibly flavorful when done right. After the tour, I was blown away by how intricate and well thought out the process is. And you know what amazed me the most? The sheer number of people involved, from engineers monitoring the equipment to tasters checking every batch. Yes, tasters. Turns out it's a real profession. Imagine having a job where you drink coffee and evaluate its taste. Isn't that the dream? Instant coffee isn't just powder in a jar. It's a monumental effort, cutting-edge technology, and a love for a drink that brings us comfort, even on the busiest days. So, next time you make yourself a cup, remember the many hands that work to deliver that aroma to you. Imagine this. One ship contains up to 20,000 tons of steel. That's the weight of 3 Eiffel Towers. But what happens when these ocean giants retire? Every year, more than 1,000 vessels are sent for recycling, and their materials find new life in bridges, cars, and even other ships. This isn't just dismantling, it's giving metal a second life. Stick around to see how this global process is changing the world. The beginning of the end, or why are ships dismantled? Ocean vessels have an expiration date. On average, that's about 25 to 30 years. After this, maintaining them becomes uneconomical and their structures unsafe. This is where a process, often called shipbreaking, begins. Remember those movie scenes where ships are shattered by waves? Well, no waves are needed here. Just welding tools, massive cranes, and teams of workers who know how to handle these metal giants. First, everything is stripped from the ship. Furniture, electronics, pipes, and cables. Even doors and windows. All of this can be recycled or reused. This process is usually carried out by hand, though sometimes specialized equipment is used. Workers physically dismantle the interior of the ship, unscrewing bolts, cutting metal pipes, removing doors, windows, and panels. It's meticulous, labor-intensive work, requiring attention to detail and strict safety protocols. Imagine this. Cables need to be carefully extracted so they can be sold as copper scrap, and chemicals, such as leftover paint or lubricants, must be safely removed. Even furniture is taken apart to salvage wood or metal components. Of course, on large shipyards, workers are aided by mechanical tools, cranes, gas cutters, and sometimes robots to handle hazardous materials. But the bulk of the work is manual labor. That's why, in countries like Bangladesh or India, where labor is cheaper, shipbreaking is so popular. This stage is crucial because properly preparing a ship for dismantling prevents leaks of chemicals and toxic materials that could harm the ecosystem. Oil, fuel, and chemicals all are drained from the ship to avoid environmental contamination. Once the ship's hull is stripped of everything unnecessary, the gas cutters take center stage. Massive, rusty steel walls, the very structures that once kept the ship afloat, are gradually turned into individual pieces of metal. Workers, dressed in protective suits, stand directly on the hull. Their cutters create bright orange sparks, flying in all directions, producing a kind of steel fireworks. It's both mesmerizing and slightly intimidating. The cutter heats the metal to such a high temperature that it literally melts. But it only looks easy. Ships aren't just piles of steel. They're labyrinths of multiple layers of metal. Sometimes workers have to cut through several layers to reach the right spot. Cutting begins with the upper decks. Large sections are first carved out, like chunks of sidewalls, decks, or even parts of the hull, which are then lifted by cranes and loaded onto platforms. From there, they're sent to factories, where the pieces are recycled into new steel or aluminum. But it's not just about cutting, it's about doing it safely. That's why the hull was cleared earlier of any leftover fuel, lubricants, or other hazardous materials. Without this step, gas cutters could trigger explosions. So, this process is not just labor, it's an art that requires strict adherence to safety rules. And of course, all this happens under the blazing sun or in humid coastal climates. Workers quickly adapt to the heat, and even sparks flying at their feet become a routine sight. In the end, they witness the transformation of a massive, once indomitable ship into mere pieces of metal. It's almost like watching a rebirth. Imagine this: those massive steel blocks that once kept a ship afloat become the foundation for new bridges, buildings, or even other ships. About 90% of a ship's materials can be recycled, and the largest share is steel. A single large ship can yield up to 20,000 tons of this metal. That's the equivalent of 3 Eiffel Towers in weight. Once the ship's hull is cut into pieces, the next thrilling phase begins: transporting the steel to factories. And trust me, it's not as simple as throwing it on a truck and driving off. These metal pieces are usually so large and heavy that they can't be moved by conventional means. Massive cranes, the kind that look like they could lift a ship themselves, dominate the scene. Their long metal arms with hooks or magnetic platforms carefully grab steel sections and lift them off the ground. It's almost like watching giant toys in action, but everything is done with surgical precision, because one mistake could be costly. After that, the steel is loaded onto huge platforms or special trucks. Regular trailers won't cut it here. You need vehicles with reinforced frames capable of bearing tons of weight. Imagine this: one section can weigh several dozen tons. Sometimes, rail cars or barges are used for transport if the factory is near a port or river. This helps cut down on delivery costs because moving steel is no cheap task. The journey to the factory can be long. For example, if a ship is dismantled somewhere in South Asia, its materials might be sent as far as Europe or America. In such cases, the metal is loaded onto ships again, but this time on cargo vessels. Full circle, right? A ship becomes raw material transported by another ship. Once at the factory, the metal is carefully weighed. Every detail matters, from the total weight to the precise composition of the metal. As different alloys require different processing, only then does the steel head to the melting stage, where its new life begins. This steel will become new construction materials. Ships continue their legacy, not in the ocean, but as skyscrapers or train tracks. But it's not just steel that's valuable. Ship components also contain aluminum, used in car and airplane manufacturing. Wooden elements, rare in modern ships but present in older ones, are restored and sold for decor. Fabric from old seats is sometimes repurposed into bags or even rugs. Isn't that cool? You buy something stylish and later find out, oh, this was on a liner that sailed the Caribbean. But it's not all smooth sailing. Ship recycling can pose environmental risks if done irresponsibly. Ever heard of Alang? It's the world's largest ship recycling yard, located in India. There, ships are literally beached and dismantled by hand. This method is cheap, but dangerous. Oil and chemicals can leak into the water, and workers often lack proper protective gear. Recently, however, the world has started paying attention to this issue. More and more ships are being recycled at specialized yards that follow strict environmental standards. For instance, in Europe, regulations require the safe storage and disposal of hazardous materials. The largest ship ever dismantled was a container vessel measuring 1,312 feet in length. Imagine taking apart such a giant. This container ship, Ever Given, became famous in 2021 after blocking the Suez Canal, though its end wasn't due to that incident. When ships of this scale are retired, they're usually sent to one of the world's biggest shipbreaking capitals. Dismantling such a vessel likely took no less than a year, because a mountain of steel, cables, equipment, and other materials is a serious challenge, even for experienced teams. Every piece must not only be cut, but also carefully moved, sorted, and shipped for recycling. At the steel plant I visited, everything starts with thoroughly inspecting the metal pieces. They're cleaned of any paint, rust, lubricants, or other impurities that could affect the quality of the steel. Watch as dozens of hands and machines work to prepare this metal for its next journey. Next, the pieces are shredded, cut into smaller parts that are easier to load into the smelting furnace. The process of cutting metal at steel plants is a spectacle in itself, like something out of a sci-fi movie. Huge workshops filled with sparks, heat, and the hum of machinery. These aren't ordinary scissors. They're powerful hydraulic presses, cutting machines, and even lasers. Each tool plays its part depending on the size and type of metal. First up are hydraulic shears. These massive machines can slice through thick steel like paper. They operate under immense pressure, thousands of tons of force that literally crush and cut the metal. Their crunch echoes throughout the workshop. For finer work, gas or plasma cutters are used. A gas cutter operates by burning fuel. Oxygen and acetylene heat the metal until it melts, and then a stream of gas cuts through it. Plasma cutters are even cooler. They create an electric arc that melts the metal, leaving a clean, precise edge. Then there are laser machines. They work with incredible precision, carving out the tiniest details. The laser beam seems to dance across the metal's surface, leaving behind a smooth, polished cut. This is the technology of the future, already in action at many factories. But this isn't just random cutting. Every step is carefully planned. Metal is sorted by thickness and type to avoid damaging equipment. Larger pieces go through specialized conveyors to the next stage, while smaller ones are sent straight to melting. For melting steel, arc furnaces are used. These massive monsters run on electricity, generating temperatures close to 3,000 degrees Fahrenheit. The metal simply melts, transforming into liquid steel. But that's not all. Special substances, known as ferroalloys, are added to the molten mass to enhance the steel's properties. Need strength? Add vanadium or chromium. Want it lightweight? Add aluminum. It's like cooking, but for engineers. Next, the steel is poured into molds, depending on what it's destined to become. These could be sheets, beams, rebar, or even wire. The castings are cooled, cut, polished, and then shipped off for new projects. Building skyscrapers, bridges, or even new ships, all of this can start with the recycled hull of an old vessel. And isn't it amazing? A ship that once carried thousands of tons of cargo across oceans can become part of a car or the frame for a modern stadium. This second life of steel feels almost magical, doesn't it? How do you build an engine that can handle temperatures over 3,200 degrees Fahrenheit and carry a Boeing jet across the ocean? Sounds like science fiction, right? But this is the reality of modern engineering. Imagine this. Every single part, from turbine blades to combustion chambers, is crafted with micrometer precision. Metals that don't melt under extreme heat and 3D printing that's changing the game. Dive into the process of creating the heart of an airplane, where every inch truly matters. This is the magic of technology. Turbofan engines that power sky giants like Boeing and Airbus planes might seem like something straight out of a sci-fi movie, but they're the pinnacle of engineering genius. So how do you take tens of thousands of parts and ingredients, almost like puzzle pieces, and turn them into these incredible machines? Ordinary metals simply won't cut it. These engines have to function in conditions where temperatures soar above 1,800 degrees Fahrenheit. That's hellishly hot, and regular steel just can't take it. Enter titanium alloys, lightweight, incredibly strong, and heat-resistant. For the hottest parts of the engine, nickel-based superalloys are used. And trust me, these are no ordinary metals. They're 21st century alchemy. Carbon fiber composites, by the way, are used in the fan blades to reduce weight while maintaining strength. This extreme heat is generated during the combustion process in the engine's combustion chamber, arguably one of the most critical components of a turbofan engine. Here's how it works. Aviation fuel, typically jet fuel, mixes with air and ignites, producing superheated gases. These gases accelerate to insane speeds and temperatures, often exceeding 1,800 degrees Fahrenheit, sometimes even reaching 2,700 degrees in modern engines. This heat is vital for achieving maximum thrust efficiency. The hotter and faster the gases, the more energy they produce to drive the turbine and propel the aircraft forward. Here lies the ultimate challenge: The engine not only needs to endure these extreme conditions, but also perform flawlessly, without a single hiccup. That's why cutting-edge materials like titanium alloys and specialized composites are a must. They can withstand both extreme heat and intense mechanical stress. You know what's truly mind-blowing about making these engines? Even individual components like turbine blades are crafted with micrometer precision. For example, blades are cast in a vacuum to ensure they're free of even the tiniest cracks. Some blades are designed with a single crystal structure, meaning the metal has zero seams. But wait, there's more. 3D printing? Yup, it's used too, especially for intricate parts that traditional casting just can't handle. Turbine blades are the heart of the engine. They operate in the hottest zone, converting the energy from the hot gases into rotational movement. First, a wax model of the blade is created. It's almost like artistic sculpting. Only here, precision down to micrometers is crucial. This wax model is then dipped into a special ceramic solution, which hardens into a strong mold. The wax inside is melted away, leaving a perfect cast for the blade. The ceramic mold is now ready for the most critical stage. Now comes the real show. Superalloys, made of nickel, chromium, and other heat-resistant metals, are melted in a special furnace to temperatures exceeding 2000 degrees Fahrenheit. This molten metal is poured into the ceramic mold. But here's the catch. It's not just about the material, it's about how it's done. To ensure the blade can handle enormous temperatures and stresses, it's often cast as a single crystal. This means the entire piece of metal has no seams, micro cracks, or grains like regular metals do. Why is this important? In these conditions, seams or cracks are like a ticking time bomb. One small flaw, and the blade fails. Single crystals are grown through a slow cooling process. The mold filled with molten metal is gradually lowered into the cooling zone of the furnace. This process can take days, but the result? A blade that's incredibly strong and durable. Once the metal cools, the ceramic mold is broken away, and the blade undergoes meticulous polishing. A special heat-resistant coating may be applied to help it withstand extreme temperatures even longer. And yes, each blade is inspected individually. Even the slightest defect means it won't make the cut. Fuel nozzles, combustion chamber parts, or even compressor blades in aviation are often made using 3D printing. For instance, GE Aviation prints fuel nozzles for its engines that are 25% lighter, but 5 times stronger than traditional ones. Layer by layer, using powder and light, components are created that make planes fly faster, farther, and more efficiently. First, engineers create a digital 3D model of the part with maximum precision. Every curve and cavity matters. Why? Because these components often operate in environments where even a millimeter can make all the difference, from engine efficiency to reliability. This digital model becomes a map for the 3D printer, which knows exactly where and how to build the required shape. Instead of a solid chunk of metal, ultra-fine powder, made from titanium, nickel, or Inconel, a super strong aluminum alloy, is used. It looks like sand, but the particles are so tiny they're almost invisible to the naked eye. The powder is loaded into a special reservoir, becoming the building material. The printer's working principle is simple yet genius. It melts the powder using a laser or an electron beam. The laser heats the powder to a temperature where it literally fuses into a solid metal structure. Then, another layer of powder is added, and the process repeats. This method is called selective laser sintering or melting. And here's the cool part. 3D printing can create even the most complex geometric shapes. For example, components with internal cooling channels that simply can't be made using traditional casting or milling. In conventional manufacturing, you often start with a big piece of metal and carve away the excess. It's not only time-consuming, but also expensive because so much material gets wasted. 3D printing flips the script. You only create what's needed, with zero waste. But the part isn't ready yet. After printing, it undergoes heat treatment, heating, and gradually cooling to relieve internal stresses in the metal. Then comes final grinding, polishing, or machining to fine-tune precision. And of course, every part undergoes rigorous testing. Because here's the thing, if a part fails under pressure, the consequences could be catastrophic. Engine assembly takes place in a massive hangar. where every inch of space is filled with tools, engine parts, and technicians in overalls, all focused on creating something extraordinary. This is the final stage of building an aircraft engine. Here, individual components, like blades, compressors, combustion chambers, and casings, come together to form a single unit capable of lifting an airplane into the sky. It all starts with the engine casing, a giant metal cylinder that serves as the skeleton, where everything else is attached. The casing is made from titanium or nickel alloys because it has to withstand insane forces. Engineers work like watchmakers. The casing is mounted on a massive rig to ensure perfect alignment. Then come the compressors, rows of blades responsible for compressing air before it enters the combustion chamber. Each blade is installed one by one, almost like decorating a giant wheel. Every single blade is manually inspected because even the tiniest defect could ruin the entire assembly. After the compressors, it's time for the turbines. These are the blades that convert gas energy into movement. They're installed with such precision that the gap between the blades and the casing is sometimes measured in micrometers. Next comes the combustion chamber, the engine's hell zone. This is where compressed air mixes with fuel and ignites. Engineers install special nozzles to ensure fuel is delivered evenly, and everything here has to be flawless. A nozzle at the wrong angle could reduce efficiency or even cause engine failure. Running through the entire engine is a central shaft, essentially the backbone. At one end of the shaft is a fan, a massive wheel at the front of the engine, and at the other end is the turbine. When the turbine spins from the force of hot gases, the shaft transfers this energy to the fan, which draws in air. Installing the shaft requires specialized robots. This part of the process demands surgical precision, as even the slightest misalignment can cause vibrations that could kill the engine. Once the engine's internal components are assembled, external systems are added. Fuel lines deliver jet fuel to the combustion chamber. The oil system ensures all moving parts are lubricated. And the electronics? The engine is packed with sensors that monitor temperature, pressure, RPMs, and much more. These systems are attached using cables, tubes, and bolts that must withstand both vibration and extreme temperatures. After assembly, the engine isn't immediately installed on a plane. First, it's mounted on a test stand that simulates real flight conditions, from takeoff to turbulence at altitudes close to 33,000 feet. This is the most spectacular stage. Running the engine at full power fills the air with a deafening roar, audible from miles away, and streams of blazing exhaust gases. The engine is pushed to its limits for hours as engineers test its strength, durability, and efficiency. Once the engine passes all tests, it's disassembled. Key components are rechecked, and then it's reassembled for final delivery. The finished engine is packed and shipped to Boeing or Airbus, where it becomes part of a new aircraft. Piece by piece, engineers craft the heart of an airplane, a marvel capable of carrying thousands of passengers across continents. Isn't this a modern masterpiece? Let us know if you'd like to see more videos like this.